So picture this. You've just spent literally weeks writing an incredibly complex, brilliant piece of software. I mean, everything is mathematically perfect. But then, a user interacts with your program and accidentally inputs a 0 where a number should be. A simple mathematical impossibility, division by 0. What actually happens to your raw code in that exact fraction of a second?
Well, if you haven't prepared for it, you get this, the dreaded crash message. The operating system just steps in, pulls the plug on your program entirely, and leaves your user staring at a broken screen. Without proper error handling, our programs don't just hiccup, They die abruptly, and in the professional world, that is absolutely not an option.
Welcome to This Explainer. Today, we're going to master the ultimate safety net for robust programming, C++ exception handling. We'll explore how modern C++ empowers us to intercept disastrous errors, gracefully recover from them, and keep our software running smoothly, no matter what kind of curveballs get thrown its way. Here's our roadmap for today. We'll look at the exception problem, try, catch, and throw, built-in exceptions, creating custom ones, and finally, rethrowing and stack unwinding. Let's dive right in.
Section 1. The exception problem. Why do older methods of checking for errors suddenly fall short when our software scales up? To really get that, we first need to define what an exception actually is. In C++, an exception is simply an occurrence of an undesirable situation that gets detected during program execution. We aren't talking about syntax errors that stop your code from compiling in the first place. We're talking about runtime bombs, like trying to open a file that doesn't exist, accessing an array index that is way out of bounds, or, like we said earlier, dividing by 0.
Back in the day, developers heavily relied on if statements or the assert function to catch these kinds of issues. But there's a huge problem with that. Assert statements are ruthless. If a condition fails, the program terminates immediately. Imagine you wrote the software monitoring a multi-million-dollar satellite in space. If a temporary power failure happens in one tiny sensor, you absolutely cannot have an assert function terminate the entire satellite's life support. We need a completely different approach. We need exceptions to gracefully handle errors, isolate the problem, and keep the main system alive and kicking.
Section 2. Try, catch, and throw.
All right, this triad right here is the core syntax that makes up our modern safety net. Think of the try block as a sort of quarantine zone. You place your risky, unpredictable code inside it. If everything goes well, the code just runs normally. But if something undesirable occurs, the try block immediately stops executing and generates an exception. And standing by directly below it are your catch blocks. These are your handlers, specifically designed to catch that generated exception and deal with it without crashing the entire program. So the absolutely crucial point here is understanding the specific roles of these keywords. The try block runs the risky code. When an error is detected, we use the keyword throw to literally toss an exception value right out of the try block. The catch block then catches that specific exception type, like an integer or a string. Finally, C++ gives us this fantastic universal net, a catch block with 3 dots inside the parentheses, known as an ellipsis. This is a catch-all that handles absolutely any type of exception. Just remember, because it catches everything, it always has to go at the very bottom of your catch list.
Let's actually see this in action. We prompt the user for a dividend and a divisor inside a try block. Now, we check if the divisor is 0. If it is, bam, we execute throw 0. The moment that throw executes, the normal flow of code halts completely. It skips the actual division calculation entirely, leaps straight out of the try block, and lands safely in the catch block that expects an integer. The program prints division by 0 and simply moves on, totally dodging a fatal crash.
Section 3. Built-in C++ exceptions.
Now, you don't always have to reinvent the wheel here. The standard library provides a really highly organized exception hierarchy in the std except header. The base parent is simply called exception. From it, we derive specific categories like logic_error, which is great for bugs like out of range when you try to access a string subscripts that just isn't there. There's also runtime_error for unpredictable execution issues like arithmetic overflows. And one you'll see a lot in heavy systems is bad alloc, which is automatically thrown by the new operator when your computer literally runs out of memory to allocate.
And all of these built-in classes share an incredibly handy feature, the .what function. When you catch a standard exception, you don't have to guess what went wrong. You just call this function on your caught exception object, and it returns a highly readable string containing an appropriate error message explaining exactly what triggered the failure. Seriously, it's a total lifesaver for debugging.
Section 4. Creating custom exception classes.
But what if you're building an application with highly specific business logic? Sometimes a generic out-of-range error just doesn't describe the reality of what's happening in your software. You want custom exceptions to deal with application-specific errors and provide highly tailored error messages. The absolute beauty of C++ is its flexibility. Literally any class can be treated as an exception class. It doesn't even need to inherit from those standard classes we just looked at. What makes a class an exception is simply the act of throwing it.
So if we create a class called division by 0, we can throw it just like any other value. We just use the syntax throw division by 0 followed by parentheses. See those parentheses? We are actually instantiating an anonymous object of our custom class right there on the fly and tossing that entire object out of the try block.
To catch it, we just set up a catch block that expects a parameter of type division by 0. Let's name that parameter div by 0 obj. Now inside the catch block, we have full access to that custom object. We can call it specific.what function, or frankly any other member functions we've designed to print our fully custom error message to the user.
This perfectly illustrates exactly how you'd build that custom class behind the scenes. It's really just a standard C++ class. We have default constructors that set a private string variable to division by 0 and an overloaded constructor that lets us pass in our own custom string. Finally, we define our own .what function to return that specific message string. It's incredibly elegant and keeps our error handling perfectly tailored to our exact logic.
Section 5. Rethrowing and stack unwinding.
Okay, so what happens when a function catches an error but isn't actually equipped to fully resolve it? In complex software, functions call other functions, which call other functions. Sometimes, a deep-level function catches an exception, logs it locally, but realizes the main application really needs to know about it to make a broader decision. Well, you don't have to handle it completely right there. You can partially process the error and then use a simple throw statement with no expression. This acts like a relay. It rethrows the exact same exception up the chain to the higher-level calling environment.
This relay method is actually the foundation of something called stack unwinding. When an exception is thrown and not caught locally, the system starts a search operation. It leaves function C, safely destroying all local variables in the process. It bubbles up to the caller, function B. If B doesn't have a catch block, it unwinds again, destroying B's local variables, bubbling all the way up until it finally finds an appropriate try/catch block, say back in your main function.
Here's stack unwinding in action. The main function calls function A inside a try block. Function A calls function B, which calls function C. But function C throws a myException object. Notice that function C has no catch block. Neither does B, neither does A. So the program methodically unwinds the stack, retreating backwards through the call chain until the exception finally crashes into the catch block all the way back up in the main function, where it's safely processed and the program survives. If it never found a catch block, the program would simply terminate.
Which leaves us with this final thought. We've seen how exceptions transform fatal errors into completely manageable detours. We've explored the try-catch syntax, the standard libraries, building custom classes, and the raw power of stack unwinding. So as you go back to your own code, the question really remains: will you build resilient safety nets that gracefully handle the unexpected, or will you let your programs crash without a trace? The choice and the stability of your software is entirely in your hands. Thank you so much for joining me on this explainer, and happy coding.